you. I don't know, is this working? Is it? Okay.
Green light? Can you see
There
the
is a green light.
Yes.
Yeah. Okay. Okay. Here is how do you go? How do I change page here? Down? Okay. Okay. So thank you for inviting me to this nice conference. And I will report on some work, some current work together with Pavel Nyoff and Nikolai Reshetykhin. Now, let me start with a short introduction, what I'm going to talk about. Well, I will give you first some introduction to the motivation for this, and then a little bit of classical Lagrangian field theory, but from some new viewpoint, which is suitable for the BV version on manifolds with boundary. And well, if there is some time at the end, I could give some comments about the quantization of this. So the idea is somehow to implement the Siegel and Atiyah's axioms in the case of perturbative quantum field theory. So let me remind you about it. So let's start first with quantum mechanics. In quantum mechanics, you have vector spaces, or actually Hilbert spaces, and operators between them. And somehow you should think that this is related to the fact that quantum mechanics is a one-dimensional theory. So somehow you should think that, well, you have just time, which is an interval, and to the endpoint of the interval, which are just points, you associate vector spaces, and to the interval itself and to the dynamics associated with the interval, you associate an operator, going from one vector space to the other, or equivalently, a vector in the tensor product of the two vector spaces associated to the boundary points. Actually, there is a reason why I don't say Hilbert spaces, but just vector spaces, because in most cases, these vectors do not really belong to Hilbert space. Actually, already in the case of quantum mechanics, if you think of your operator going from a Hilbert space to the other Hilbert space, it's okay. But if you think of it as a vector in the tensor product, it's usually not really a vector in the Hilbert space, because it's a unitary operator, so it's not a Hilbert-Schmidt operator. So for this talk, we only talk about vector spaces. We forget the Hilbert structure. So Siegel generalized it to field theory, higher dimensional things. So now the idea is that you're working with manifolds with boundary, and the idea that to each boundary component, or actually to the whole boundary, you associate some vector space, and to the bulk, to your manifolds or to your cobordism, you associate a vector in this Hilbert space associated to the boundary. That's somehow the idea. And then gluing manifolds along common boundary corresponds to just somehow taking inner product of well, the component of the vector in the corresponding vector space associated to that boundary component. These general axiomatics found an incarnation, for example, in conformal field theory, and in topological field theory. This is Atiyah's version, where in addition you put the condition, the extra axiom, that the vector associated to the cobordism is invariant under a diffeomorphism, preserving the boundary. And this was also realized, in some sense, in a non-perturbative way in Chern-Simons theory, or actually in the theory that the non-perturbative theory that is supposed to correspond to Chern-Simons theory. This is called Reshetykhin-Turayev invariant for free manifolds. Now, the point is that actually, when you start with just a Lagrangian, as in field theory, as physicists do, usually you don't have any clue on how to quantize this in a non-perturbative way. It happens that in Chern-Simons theory, you have a recipe that looks like what the non-perturbative theory should be, but in general, you don't have this. So what you actually have, and that's actually what physicists do in all computations related to experiments, is a perturbation theory. Somehow you just assume that just perturbation theory around the Gaussian makes sense, even if this Gaussian integral is infinite dimensional, but you just take this as a definition, and then you just go on and you check that whatever you get is non-ambiguous. And I mean, there is, and it is actually non-ambiguous. Now, the idea is now to implement these axioms in the case of perturbative field theory. Now, a lot of things change. For example, the vector space associated to the boundary now turns out to be, okay, in the simplest possible case, spaces of function on infinite dimensional manifolds, for example. And another problem is that usually, I mean, interesting theory have symmetries. For example, Chern-Simons theory has symmetries. And in the non-perturbative version, what happens is that first what you do is just quotient by the symmetries. So at the end, you get to work with some nicer symplectic manifolds, and which actually, well, may be singular but finite dimensional. That's what happens in topological field theory. However, if you do this perturbation theory, I mean, you cannot get rid of the infinite dimensionality at the beginning. So you have to keep track of everything. Okay, so this is somehow the goal, and the way that in which symmetries are kept into account in a nice way that also compatible with the boundaries, is a called BV formalism that we will introduce in the second part of the talk. So in the first part, I will just make an overview of classical Lagrangian field theory, something you should find in textbooks, in undergraduate textbooks, but somehow in a slightly more modern way, which is compatible with what I'm going to do in the second part. So just let me start with the simplest example, just Lagrangian mechanics in one-dimensional. So you're just given some Lagrangian, for example, the usual one, kinetic energy minus potential energy. So L is a function, in this example, is a function of a tangent bundle of some manifold n. There is some metric by which you can define the north square of the velocity, the tangent vectors, and then there is some prescribed function v, the potential function. So L is such a function. And then for every path, taking values in n, you can associate a number, which is just the integral of this Lagrangian evaluated on the path. So S, the action, is a function on the path space. And then the classical thing is just you look for the critical points of this functional on this path space. The critical points are called Euler Lagrange equation, and in the case of this Lagrangian, you recover Newton equation, just mass times acceleration equal to force. The force is just the gradient of v. Now, the classical theory of differential equation tells you that in this nice situation, a solution uniquely specified by initial condition, initial position, and initial velocity. So Tn appears again as a space of initial conditions. So notice that this example, Tn appears twice. It is the space in which the Lagrangian is defined, but it is also the space of initial condition. This is peculiar of this example only. So it will not be the case in any other example. Now, there is one caveat. When you compute the critical points, you have to integrate by parts. And so usually what you do is that you fix some boundary conditions such that the boundary term are 0 by definition. If you don't do this, actually what you get is some, there is a stick or, okay, no, we just put it out there. So what you get is something different. So mainly, if you take the variation of the action, you get some bulk term, which I call EL. There is something. Which I call EL. So this is an integral over the interval again, with some function on the integral. And basically, this contains the Euler Lagrange equation, plus some boundary terms, which comes out from integration by parts. So this alpha is actually a one form defined on the space of initial condition, Tn. So you just take the derivative of the Lagrangian with respect to the velocity and multiply by the differential of the coordinates. And that's an easy exercise to show that this is actually globally well-defined one form. This goes back at least to Noether, maybe even before. So now the general equation is this. The variation of the action is some bulk term, which contains the interesting equation of motion, plus a boundary term, which is this canonically defined one form. And the idea is to generalize this to other situations, either higher dimensional theories or theories with symmetries. Okay, then to go on. Well, the interesting thing that you have this one form alpha. So the natural thing is to take this differential. This is a two form, and in the example I just described, this two form is non-degenerate. So this gives you a symplectic structure on the tangent bundle of the manifold. Actually, what you can see more, that basically you can reformulate what I said so far by starting with any function L, any Lagrangian, not necessarily a good one. And it turns out that this two form is precisely non-degenerate if this Lagrangian is non-degenerate, which means that the Hessian with respect to the velocity is non-degenerate. Now, this is not the usual way you describe the symplectic structure associated to a mechanical problem. Usually, you prefer to work on the cotangent bundle, which possesses a canonical symplectic form. And in this case, this symplectic form is just a pullback of the canonical symplectic form by the Legendre mapping, which is defined using the Lagrangian. And again, this Legendre mapping turns out to be a local diffeomorphism if and only if the Lagrangian is regular, which is if and only if this two form is non-degenerate. So the point that we want to go beyond. We don't want to make this assumption that the Lagrangian is non-degenerate. Okay, then what you do, you take your equation of motion, you solve them, you get in the nice situation of Newton's equation, you get the flow. And one thing you can do, you can take the graph of this flow as a submanifold of tangent bundle cross tangent bundle. Here, just change the sign of the symplectic form. And since this flow is a symplectomorphism, this graph turns out to be a Lagrangian submanifold. So this is the point. Now, the first remark is that this L may be defined equivalently in a different way, which we can use for generalization. So the idea is the following. First of all, we have a map from the path space to two copies of the tangent bundle. Just compute position and velocity at the two endpoints. Inside the path space, you have the solutions. So I will note this by EL. EL is a subset, often a submanifold of the path space, which contains solutions. And then you just project the solution to Tn cross Tn. And in this case, you can check that this gives you back the same L. But now the point that this is more general. For this, you don't have really to assume whatever I've written here. You can do it in general. You start with any Lagrangian. You compute the other Lagrange equation, and you project them over here, and you get some subset, often a submanifold. And this is the thing we are interested in. Now, let me describe another example where the Lagrangian is degenerate. This is very simple geometrically, but that's a nice feature. So this is an example of geodesics on the Euclidean plane. So the Lagrangian, in this case, is just the norm of the velocity, the Euclidean norm of the velocity, not norm square. So the main difference now that the action is invariant under parametrization. To make things non-degenerate, instead of taking the whole path space, we just take the space of immersed paths. We don't want velocity equal to 0. This would be a bit singular. But apart of this, we can go on. For example, we can compute the critical point that turn out to be straight lines or straight segments. Now, what is the space of initial data? Well, this is a bit tricky because we are talking about parametrized straight segments. So, of course, you cannot specify a unique parametrized straight segments in terms of initial data. But at least in a formal neighborhood, you can. So the only thing you have to give is the initial position and all derivatives. They are all jets. So now the space of initial data is infinite dimensional. And the all important thing is that velocity, so this R2 is the position, this second R2 is velocity, and these are infinite, all higher derivatives. And the important thing that we want to remove velocity equal to 0. So actually, we'll rewrite this R2 minus 0 in polar coordinate as S1 cross positive numbers. And I will denote coordinate by this letter. So Q is the position, V is the normalized velocity, rho is the modulo of the velocity, and these Q's are higher derivatives. Now, if you compute the one form by the rule I gave you before, so just take the derivative of this with respect to velocity times dq, you get that the one form is this one. So now this is clearly, the two form is clearly degenerate, because it does not depend on the Q's, it does not depend on rho, so clearly it is degenerate. But on the other hand, you can define this L, actually we'll not L twiddle here, as a projection of EL. So EL are straight lines. You project on two copies of this boundary space, and this turns out to be this subset. So basically, okay, the first observation that the initial normalized velocity is equal to the final normalized velocity, the same V. Rho, I mean, the modulus of the velocity can change. Higher derivatives can change. The initial position is not the same as the final position, but their difference is parallel to velocity. So we move to this. So this is exactly what you get. And the first remark is that this subset is no longer a graph. In the previous example, it was a graph of a flow. Now this is clearly not a graph, because, for example, Q2 is not determined by Q1. On the other hand, if you restrict the two form to this, it is 0. So this L3 is still isotropic. And actually, you can check that it's even Lagrangian. Now, Lagrangian makes sense even if you have a degenerate two-form, because just you can define the orthogonal space using the two-form. And the definition of Lagrangian submanifold or the Lagrangian subspace for me will be just that the orthogonal is equal to the subspace. This makes sense even if the form is degenerate. Well, usually in this kind of example, what you do is to take reduction. So you see that this two-form is degenerate, but okay, what you do, you compute its kernel, and it's very easy to see what the kernel is. So first of all, this does not depend on rho and the higher q's, so all these vector fields are in the kernel of this two-form. And in addition, there is this vector field. Essentially, you displace your position in the direction of the velocity. This also belongs to the kernel. If you take the quotient, you get a symplectic manifold, and this symplectic manifold turns out to be the tangent space of S1. So coordinates on this S1 are the velocity, the normalized velocities. And the tangent bundle is what is left of position after this quotient. And the symplectic structure here is obtained from the cotangent bundle of S1, not by pullback by the Lagrangian transform, but by pullback using the induced metric on S1. Euclidean structure gives a metric on S1, and by this you can pull back the canonical symplectic form from the cotangent bundle to the tangent bundle. And you can project down this L-twiddle over here, and here it's still Lagrangian, but actually very trivial. It's just the graph of the identity. And the reason is that this action was invariant under reparametrization, so basically it means that there is no time evolution at all. So this is an example of topological field theory. But okay, since it's one-dimensional, it's very trivial. And okay, you can somehow study modification of this example. For example, you can take more physical version where you take some Minkowski metric instead of a Euclidean metric. You repeat the example. The only difference, also in higher dimension, the only difference at the end, after reduction, what you get is a tangent bundle of hyperbolic space. Okay, that's it. Now, in principle, you could proceed this way, but in practice, what happens in most examples is that this quotient is very singular. So the idea is that it's bad to take this quotient. So you have to find some way around. Now let me give you one more one-dimensional example. This is about the so-called one-dimensional Polyakov action. So the idea is the following. Now here there are two fields, x and y. X is a path in R, and y, well, it's also a path, but it's strictly non-negative. Actually, you should think of x as a path and y, or actually one of this y square as a metric on the interval. So this it's about the cosmological constant, and this is the metric-dependent term for the velocity. Now you can repeat the same exercise I did so far. Actually, one remark is that for lambda greater than 0, this is practically equivalent to the previous example. But this actually makes sense also for lambda equal to 0 and for lambda negative. Now for lambda negative, it turns out that there are no critical points, but still you can consider it. Now if you repeat the example, it turns out that first of all you can define the one form, or we can define the initial position, you can define the one form in the space of initial conditions, and you can also take the reduction. So the reduced space turns out to be just R2 with the canonical symplectic form, actually with the canonical one form. And the projection from the space of fields to the boundary turns out to be, roughly speaking, evaluating position and velocity, but somehow you have to correct by these y's at the end points. This turns out to be the correct projection. Now you can do the exercise. You can compute critical points and project. And it turns out that for lambda greater than 0, the L in the reduced space is Lagrangian, but not a graph. In the previous example, it was the graph of the identity after reduction. Here, even after reduction, it's not a graph, but still Lagrangian. In the case lambda equal to 0, things are a bit subtler, because what you get is not a graph. Actually, yeah, it's not a graph, but in addition, it's not even Lagrangian. It's just some isotropic. So this somehow tells you, I mean, these two examples tell you all kinds of pathologies you can find out. And maybe just let me give one more example. This is a two-dimensional example. So this is already field theory, but without symmetry. So this is just a scalar field in 2 dimensions. So you fix some metric on some manifold M, your fields are functions on M, and your action is just this integral. So here you use the metric to construct indices. Now the critical points are just harmonic functions with respect to this metric. And so suppose that I do it in 2 dimensions just to simplify the intuition. So the boundary is just a collection of circles. And basically the data you have to give on the boundary are just the fields on the boundary and its normal derivative. So okay, let's see that for simplicity I assume that I have a Riemannian metric. Okay, and then okay, you can project your fields to the boundary. You just compute the fields, the restriction of fields on the boundary and the normal derivative. And you can compute the other solution to all the Lagrangian equations, such as harmonic functions, and project to the boundary. And it's an easy exercise to show that this is Lagrangian indeed, but not a graph in general. It's a graph if you consider a cylinder, but if you consider a more complicated manifold with boundary, it's not a graph. But you can check it is Lagrangian. Now this is true if you take a Riemannian metric. If you try to repeat this exercise with a pseudo-Riemannian metric, it turns out that depending actually on which manifold you take, you might get non-Lagrangian submanifolds associated to the boundary. Okay. Now, after these examples, I want to present the general theory. In principle, this should be very old. It goes back to the 18th century, but somehow it was developed very slowly. There are some recent accounts in the 90s by Gavezzi, Schwarz, and some unpublished account by Fock. And I mean, I will give you some presentation of this. Actually, our version of this presentation, which is compatible with the Batani-Wilkowicki formulas, I will have to use in the second part. So the idea is the following. So a Lagrangian field theory for me is given as the following. So first of all, you fix a dimension D on which you want to define the theory. And then you define some local, you define some space of fields, which could be, for example, functions on this manifold, or section on some vector bundle of these manifolds, connections for these manifolds. I mean, essentially something local. So essentially, you need some sheaf, around section of some sheaf. And then the Lagrangian is something that is defined on local data. So this really just depends on the dimension, but does not depend on which manifold you are really considering. Now, once you're given a manifold, you can integrate this Lagrangian. Well, you should either think of this Lagrangian as taking values in densities, or you assume there is some metric, so that you can define a volume element. But then you have an action that depends on the manifold. So once you fix your data, you have a function. I mean, you have an action for each manifold, for each d-dimensional manifold. Okay. Then how you define the boundary data? Well, the easiest way is just pick any d-1 dimensional manifold and make it artificially into a d-manifold just by multiplying by an interval. So now you have the fields on this surface sigma, the d-1 manifold sigma cross an interval, right? And basically, you just take jets around 0 as fields associated to the boundary. Now, your action allows you to define a one form on this space. Essentially, well, you just have to take into account all possible terms that come out from integration by parts. Actually, there is an explicit formula in terms of jets. So there is a well-defined one form on this space. And now, but by construction, whenever you take the variation of your action as associated to some manifold M with boundary, you get some bulk term, which actually contain the Lagrangian equation, plus some boundary term. So this pi m twiddle is a projection from the bulk field to the boundary field. You just evaluate jets on the boundary. And this one form alpha twiddle is well defined over here. Now, the natural thing to do is to take the differential of this one form. This will define some two form on this space F twiddle sigma. And now the crucial assumption is that this two form is well behaved. We don't require it to be symplectic, but we require its kernel to behave well. So in finite dimension, the requirement is the kernel has the same rank at every point. The infinite dimensional version, of course, is a bit, well, this doesn't make sense. So the correct definition that you want the kernel of these two form to be really a sub-bundle of the tangent bundle of your infinite dimensional space. So this means that this locally you can define the quotient and get a symplectic structure. Now, let's do this quotient. And by simplicity, I will assume that this quotient is really a manifold. Okay? So this is a symplectic manifold, because you can use a symplectic structure. So now to the boundary, you can associate now a symplectic manifold, which in general is still infinite dimensional. And now for simplicity, this is not really necessary. I will assume that the one form itself descends. This is not really necessary. Actually, there are several interesting examples where this is not the case, but this simplifies the discussion. Actually, what generally happens is that you should think of this one form actually as a connection for a line bundle, and what you should require is that this connection descends, not as a one form, but as a connection. So this is a milder condition. Still not general, but this is a much milder condition. Okay, but under this simplifying assumption, the symplectic structure on the quotient is exact, is a differential of this one form. And you still have this equation. Now, this pi m is a composition of the two projections. One is the restriction of fields to the boundary, taking all jets. And the second one is a projection from this f twiddle to its quotient. So this is still a surjective submersion, and you still have this equation. Variation of the action is some bulk term plus the pullback of this one form associated with the boundary. Now, this equation is quite interesting because suppose that you take the set of solution to the other Lagrangian equation, which is just the zero set of this one form, project it to the boundary, define this Lm. For simplicity, I will assume that whatever subset I consider here are really submanifolds. But this equation immediately tells you that this submanifold is isotropic, namely the two form omega restricted to it is 0. And the reason why, basically, you see it here, right? This term disappears. So this means that essentially when you restrict the one form, it becomes exact. So its differential is 0. Now, something that is not true in all examples, or the same example, but we are going to assume is that this Lm is not just isotropic, but really Lagrangian. This is a crucial assumption. Actually, it's a physical assumption. There are some reasons for it. At the classical level, the reason is that you want to recover the dynamics by specifying boundary conditions. And the idea is that you have this canonically defined Lm. And what you do, you specify general boundary condition consists of another Lagrangian submanifold that is transversal to it. And then you just look at the intersection point. Generically, you just have points. So for this to make sense, you have to assume that this is really maximal. Otherwise, you run into trouble because well, either you don't have uniqueness, or you have to specify boundary conditions that are more than Lagrangian. And this gives you other problems, because they cannot be either isotropic. An interesting remark is that if this condition actually selects theory. So for example, if you take, I mean, okay, not similar, but to me, for example, there are Yang-Mills theory, Chern-Simon theory, maybe people here know Chern-Simon theory. These are based on some Lie algebra. Now, actually, you can just take the Lagrangian of this theory and replace the structure constant of the Lie algebra by just some arbitrarily given numbers. They make sense as Lagrangian field theory, but the moment you compute this Lm, you realize that in general, this is not Lagrangian. And actually, a nice exercise that these Lm are Lagrangian if and only if you're really working with the structure constant of a Lie algebra. So this really tells you why Lie algebra should enter into the picture. For those who know the so-called Poisson sigma model, even there, you can replace a Poisson tensor by an arbitrary tensor, and it turns out that in general you don't get a Lagrangian submanifold. Actually, you get a Lagrangian submanifold if and only if your tensor is Poisson. So this condition is also interesting because it selects in this example. The next thing you can define is this C sigma. So this C sigma, again, you take some d-1 dimensional manifold sigma, you make it d-dimensional by multiplying by some interval. Then you have a Lagrangian inside the space of fields associated to sigma. And the idea is that now take, okay, you have this space of boundary fields associated with the d-1 manifold sigma, and you take all the points that can be completed to a pair that belongs to one of these Lagrangian. for some interval, no matter how long it is. And again, it's an easy exercise in symplectic geometry to show that this C sigma is quasotropic. If you assume that the L's are Lagrangian, this C sigma turns out to be quasotropic. So this means that the orthogonal to the tangent space is contained in the tangent space itself. And this somehow is a correct space of Cauchy data for the problem. Actually, at this point, the correct thing to do would be, from a geometrical point of view, to do the reduction. You have this quasotropic submanifold, you quotient out by the kernel of a symplectic form. If this quotient is smooth, it's automatically symplectic. Then you can project down your Lagrangian over here. And this will give you some Lagrangian submanifold, this symplectic manifold. And now everything works as you expect. The problem is that these quotients are usually very, very singular. Basically, in almost every theory, they're very singular. So the idea is to avoid doing this quotient. OK, maybe just to finish the discussion, in the usual example, say, of Newtonian mechanics, you also have composition. You can compose flows. How is composition defined here? Well, basically, you just compose these Lagrangian submanifolds. These are just submanifolds, actually subsets of Cartesian products. So they are just relations. And you compose them as relations. So an element in the composition is just a pair of elements such that you can find a third element in the middle space such that both pairs belong to the relation. That's just a theoretical composition of relations. And, well, the easy exercise is that whenever you can glue two manifolds with boundary along a common boundary component, you can either compute the Lagrangian associated to the glued manifold or the separate Lagrangian and compose them as a relation, you get the same answer. This is, well, looks abstract, but it's very, very simple. It just means that the solution on the glued manifold are just a solution, when restricted to the components, and they have to match on sigma. Nothing more than that. So for this reason, we call this Lagrangian the evolution relation. This somehow replaces the flow. Okay, just one remark that sometimes it's better to keep track not just of the image of the projection from EL to the boundary, but actually of the fiber, because well, this construction guarantees uniqueness only locally. So for very short cylinders, so if you take more complicated manifolds, you cannot expect uniqueness. So somehow there is some information in the fiber itself. So for this point of view, instead of just taking these Lagrangian relations, it's better to think in terms of correspondences. But OK, this if you want to keep track of everything. And maybe just let me finish with the abstract definition of gauge theory in this setting. Basically, we say that we have a gauge theory whenever this C sigma is quasotropic, but in some cases it's really symplectic by itself. So in this case, we don't have a gauge theory. So we speak of a gauge theory when really the two form on this quasotropic submanifold is degenerate. So there is some quotient to be taken into account. So this is a general definition of gauge theory, and then the idea that somehow you should take the quotient, the symplectic reduction of this manifold, needs now to be actually the same as quotient in this quasotropic submanifold by the relation that is given by considering infinitesimally short cylinders. This is the equivalent, and somehow, okay, the reduced picture has no longer symmetry, but usually is very singular. So again, we don't want to do that. Okay, now let me summarize what how we can formulate Lagrangian field theory. So remind you that we start just by thinking of Lagrangian field theory given in terms of a local Lagrangian function. But this construction at the end gives a completely different description, which is reminiscent of the Siegel's action, but in the classical version. So the idea is that, so we fix a dimension D. Now, for every dimension, for every d-dimensional manifold M, possibly with boundary, we have a space of fields. And for every d-1 manifold sigma, we have another space of fields, which is symplectic. And then, whenever a bulk, we have a Lagrangian correspondence, or if you forget the fiber, just a Lagrangian submanifold. So and in addition, these things, the association is compatible with gluing. So really, you should think of this as a functor from the category of cobordism, of d-dimensional manifold, to the extended symplectic category, where objects are symplectic manifolds and morphism are Lagrangian submanifold of Cartesian products. Of course, everything is in quotation mark. The extended symplectic category is not a category, because the composition of Lagrangian submanifold in general are not a submanifold. And in addition, you have to say exactly what is the cobordism category. And here, it depends on which kind of theory you're considering. If you have theory where, for example, you're given a metric, you really may think of having really some well-defined cylinders around the boundary. So in this case, you define the cobordism category by really gluing. But for example, for topological field theory, you don't want to do that. So you don't have a canonical way of gluing manifolds into manifolds. And so you have to do, okay, you have to use some weak version of this category like in Lurie, but it just can mimic the usual definition. Okay, now let me tell you something about quantization if there are no symmetries. Then we finally move to the second part of the talk where we see what happens if there are symmetries. So if there are no symmetry, what I assume that essentially this coisotropic submanifold associated to the boundary is actually the whole boundary space, so there is no reduction involved. So you have some symplectic manifold associated to the boundary. And I assume, for simplicity, I can do geometric quantization the simplest possible way. So what I do is the following. I assume that this symplectic manifold associated to the boundary can be endowed with a Lagrangian foliation. So just a subbundle such that each fiber is Lagrangian, with the additional property that the restriction of the one form to the leaves vanishes, and in addition that the quotient by this distribution is a smooth manifold. So in this setting, geometric quantization just tells you that the vector space you should associate to this symplectic manifold is just a space of functions on this quotient. Okay, if you want to give a Hilbert structure, take space of square integral functions, but okay, just to simplicity, just take functions. Okay, let me denote by P the projection from this boundary symplectic manifold to the quotient by the Lagrangian foliation. And then, so the recipe for getting the state associated to the bulk in perturbation theory is the following. So the state associated to the bulk should be a function of the space Bm. So you pick some point in Bm, some point phi, take its pre-image, so this is in C, take its pre-image under map pi, so this is a subset of the space of fields of the bulk, and then take the integral of the exponential of the action by, okay, that's just this extra factor, over fields that are in this pre-image. So this turns out to be a function here. Okay, the problem with this expression is that this is an integral of an infinite dimensional space, unless you are in one-dimensional example, but you can define it in perturbation theory. So the definition is not a theorem, it's still a definition. You have to look for the critical point of the action, assume that the Hessian is non-degenerate, so then you have some Gaussian integral plus perturbation, and you define this integral really as the algebraic formula that gives you the perturbation around the Gaussian integral. And well, then this psi turns out to have the good properties. So it's a vector in the vector space associated to the boundary, and whenever you glue along boundary components, the new vector is obtained by pairing the vector associated to the boundary component. So this, okay, you have to take into account renormalization and so on, but apart from this, well, very difficult technical issues, this makes sense without symmetries. Now, what happens if you have symmetries? Well, the main problem is not just that you have to do a quotient on the boundary, but also that the Hessian around critical point is now degenerate. So this procedure, this formal procedure of perturbing around the Gaussian integral does no longer make sense. So the correct procedure would be to take a quotient also in the bulk fields so that you make the Hessian non-degenerate. So this would be the geometrical picture, but of course this is no longer compatible with this nice algebraic definition of the integral. So the idea that goes back to Faddeev-Popov and then was refined by BRST and BV is to replace this quotient by something in some sense equivalent that is cohomological. So instead of going to the quotient, you enlarge your space of fields by adding some odd coordinates, and okay, you replace the quotient by taking some subspace of this enlarged space of fields. Now, I will not explain how to get there. I just give you some axiomatic definition you can just accept as a set of axioms. That makes sense. So what I have to introduce is a notion of a BV manifold. So a BV manifold is just the following triple. So F, okay, here, okay, everything is labeled by M because I consider the BV manifold associated to some manifold M on which you want to formulate your field theory, but abstractly you can define the BV manifold as following. First, you have a supermanifold F. So supermanifold, well, we already mentioned yesterday in Dimitri Rothenberg talk, essentially means that in addition to the usual commutative coordinates, you have some anti-commutative coordinates. Okay, more precisely, it means that you actually have a sheaf over an ordinary manifold, such that sections form an algebra, and this algebra is a tensor, locally is a tensor product of the algebra smooth function, tensor, and some exterior algebra. Nothing more than that. This supermanifold is actually equipped with an additional Z grading, which is important for several considerations. And well, this also was mentioned yesterday in Dimitri Rothenberg's talk. Okay, you have to be careful if you want to make this correct, but essentially it just means that you associate some extra Z grading to each coordinate. The second piece of data is a symplectic form on this supermanifold, but this symplectic form must have degree -1 with respect to the Z grading, and it must be odd with respect to the super grading. Okay, but still it's closed and non-degenerate. So in this sense, it is symplectic. And the third piece of data is a function S of degree 0, even and of degree 0. So these are all the data. And then the only axiom is that the Poisson bracket of this function with itself is 0. Now, in the finite dimensional case, so if F finite dimensional, this bracket is just defined by the symplectic structure in the usual way. And okay, you just require this condition. This condition is non-trivial because the function is even, but the bracket is odd. So this is a Maurer-Cartan element in this setting. Well, shift degrees. Another way of writing this equation is the following. First of all, you compute Hamiltonian vector fields associated to this function. So this is the unique vector field that contracted with symplectic form gives you the differential of the function, right? And then this equation just says that this vector field applied to the function is 0. And in particular, it turns out that this vector field commutes with itself. This is just the Lie bracket of vector fields. So this Q now defines a differential on the algebra of functions. And this is called a cohomological vector field. Now, in the infinite dimensional setting, it's almost exactly the same. The only point is the Poisson bracket is not defined for all functions. So somehow this condition now is the union of these two conditions. So the first condition is that the differential of your function is in the image of the symplectic form. So there is a Hamiltonian vector field, which is by definition unique, because this is a non-degeneracy condition. And then the second condition that apply the vector field to the function gives 0. So this is how you define this bracket. So this makes sense also in the infinite dimensional case. Now, the procedure is that now, if you want to define the field theory, d-dimensional field theory with symmetries, to each d-manifold M, you associate a space of fields, I mean superspace of fields this way, symplectic form and the function, satisfying this condition. Now, everything is local here because you start with a local field theory. So that's essentially the main theorem by Batan and Vilkovisky is that under some mild non-degeneracy condition, you can always do that. So now we start this. We assume that we have this data. And the important thing that is omega, and this, so everything is local. So this supermanifold is actually a manifold of local things like maps or sections of vector bundles, things like that. And both omega and S are local in the sense that they are integral over the manifold of some function of local jets of the fields. That's the field. So the point is that then this equation actually makes sense only if the manifold has no boundary. Because here you see we have the same problem, right? This ds is actually the variation of the action. So you have to integrate by parts. So you might have boundary points. So now we have to solve this problem, and somehow the solution, well, is the same as what we discussed in the classical case. So how does it work? Basically, we repeat what we did so far. So now again, you take a D minus one dimensional manifold sigma, you make it into D manifold by multiplying by an interval, you define a space of boundary fields just as jets around 0. You compute the corresponding one form. So this one form is determined by the action, not by the symplectic form. Again, assume that its differential is presymplectic, assume that the quotient is smooth. So now we have a symplectic, supersymplectic manifold associated to the boundary. So far, the only difference with the previous case that now everything is super. So now you have this super manifold of boundary fields, and you have this symplectic form, which now is even at of degree 0. Okay? But now you can use the extra data, and I mean the fact that you have this action Sm and the corresponding homological vector fields. And now if you put everything together, you can check, this is just a consequence of the construction, it's not an assumption, you can check that this homological vector field Q is actually projectable. So there is a unique, well-defined vector field on the space of boundary fields, which is a projection of this Q. This boundary vector fields, in addition, turns out to be Hamiltonian with respect to the boundary symplectic structure, and still to be homological, that is to commute with itself. So such a triple, supermanifold, symplectic structure, even and of degree 0, and Hamiltonian vector field of degree 1 that decommutes with itself, is called a BFV manifold, and is known to be a description of reduction of quadratropic submanifolds. So now we recover this way indirectly a description of the reduction of this quadratropic submanifold associated to the boundary. In addition, we now have this equation. Now, essentially putting together the two constructions we've seen so far, we have this condition. Now, this is the action associated to the bulk. This is the odd symplectic structure associated to the bulk. This is a homological vector field associated to the bulk. And this equation tells you that this Q is no longer Hamiltonian, but it's Hamiltonian up to this boundary term. So this now is a nice equation. Now, let me just make one example to show you how this really works. And then we go on discussing the consequences of this formalism. So the example is a Maxwell equation. So formulated in the more mathematical way. So the field is a connection one form A, and the Maxwell equation are just d star dA equal to 0. So A is a connection on some manifold on which you are given some Riemannian structure, and d star is computed, is a joint computed using the Hodge dual. Now, an equivalent way of describing this, which simplifies the discussion, is called first-order formalism. So you add a new field B. So now in this theory, you think you have two fields. One field is a connection A on your manifold, and the other field is a D minus 2 form B. Right? So if you have a D minus 2 form, for example, you can consider this term. B times dA is a D form, so you can integrate. And in addition, you put this extra term, B star B. Star is a Hodge dual. This can also be integrated. And you think of this as the action on this enlarged space of fields. If you look for the critical points, you see that you get this equation. Namely, B is completely determined by A, and it must satisfy this equation. So if you put the two equations together, you get again this equation for A. So this is equivalent in this sense. You get the same solution. Now, the corresponding BV action that takes into account of the symmetries, well, I don't tell you how to get to it. Just buy this as a starting point for the construction, means that now you have this graded supermanifold. So the fields here are your connection 1 form A, the D minus 2 form B, a 0 form C, which means assigned degree 1, plus the canonical conjugate fields so that you can make this into an odd symplectic manifold. So this A dagger will be a D-1 form of degree -1. This will be a 2 form of degree -1, and this C dagger will be a D form of degree +2, just to get the correct of degree +2, or degree 0, so that you can get the correct degree. And then as action, you take this. So this is the original classical action plus this extra term. So this extra term encodes the gauge symmetry, namely that you can shift your connection by an exact form. Now, if you compute the Hamiltonian vector field Q associated to it, applying to the fields, you can think of coordinates on this space of fields, you get this equation. So here you see essentially the gauge transformation for A, plus some other terms. Now, if you do the construction for the boundary, it turns out that basically what you see on the boundary are just the restriction of the field A, the field B, the field A dagger, and the field C. You don't see the other fields. And then you can compute the structure on the boundary. You can compute the one form of the boundary. You can compute the projection of the cohomological vector field and the corresponding Hamiltonian function. And now you can reinterpret this. Well, if you read this equation, basically you see that the field of degree 0 on the boundary, so these are supposed to be the classical fields are A and B. So A is actually the vector potential on the boundary, and B is related to the electric field. And then, well, if you look at this equation tells you that the vector potential can be transformed by gauge transformation, adding the exact form, and these two forms, this form associated to the electric field must be closed. So this is just the Gauss law in electromagnetism. Okay, now let's go back to the general theory. So, but basically the general theory is built around this equation. This equation has a lot of simple algebraic consequences. Maybe the most important one is this one. Basically, you can define some sense as a Poisson bracket of the bulk action with itself. I put in quotation mark because you don't have this Poisson bracket really, but by this I just mean the application of the vector field Qm to Sm, and you can see that this is just the same thing as contracting this is just the pullback of the boundary action up to this factor 2. There are some geometrical consequences, namely that first of all you can take the zeros of Qm. This is a new definition of all the Lagrange fields, project them to the boundary, and you get some isotropic submanifold of the boundary fields. And again, the main assumption that this should be Lagrangian. And then you can do some more geometry. For example, well, suppose that you could really do reduction. What you turn out to have at the end is a Lagrangian submanifold, but also vibration over it. And the fibers turned out to be symplectic manifolds of degree -1. So this is actually what you would expect out of derived geometry. Derived intersection of Lagrangians really gives you Lagrangian with -1 symplectic manifolds as fibers. So for example, you can do this in the case of electromagnetism. You get this direct sum of cohomologies. You get a mixture of absolute cohomology and relative cohomology. Now, the interesting thing is that you can actually go on to boundaries of boundary if you have a manifold with corner. So the only assumption you have to do is that the space of boundary field still looks local, and the boundary action and the boundary symplectic form looks local. And then you can just repeat verbatim the construction we did for the bulk, and you associate now some structure to D-1 two-dimensional manifolds, and so on. So somehow this tells you how to construct some sort of extended field series. And I mean, you can do this in general. The point is that very often what happens at some point, you get some trivial structure on the boundary, on some higher codimension boundary, and it turns out the fibers after reduction turns out to be infinite dimensional. So in this case, I mean, going to high codimension boundary doesn't give you much because you end up having these infinite dimensional fibers. The situation is very interesting when you keep having finite dimensional fibers, and this is, for example, the case of topological field theories, where you can really go up to the dimension 0. But for example, you can try to do this yeah, in the case of electromagnetism, well, I will do the example, but basically, essentially, if you go to codimension 2, you can compute the fibers after reduction. They turn out to be this space. Notice that these spaces, these are cohomologies, but these are not cohomologies. They are just closed forms, and these are force module exact forms. So in general, these things are infinite dimensional, unless you start in dimension 2. So if you do electromagnetism in dimension 2, this space is also turns out to be finite dimensional. So this tells you that electromagnetism in dimension 2 has a nice property that you can go down up to dimension 0. So it behaves almost like a topological field theory. Okay, now maybe just let me tell you the last thing. How do you expect to do quantization? Well, the idea is similar to the previous one. You just integrate the exponential of the action, trying to get function associated to a quotient of the supersymplectic manifold associated to the boundary by some Lagrangian foliation. The only difference that, okay, this goes into the so-called Battani-Vilkovisky formalism. Instead of integrating over the whole fibers over this point, you have just to integrate over some arbitrarily chosen Lagrangian submanifold. And the whole formalism ensures you that the result doesn't change if you deform this Lagrangian submanifold. So this picture. But then at the end, what you get now is, again, a state associated to the boundary. And this state turns out to be annihilated by some operator. Now you have some operator associated to the boundary, because the boundary is assigned a symplectic manifold, so you assume you can quantize it. But in addition, you have this boundary action, I mean the generating function for the boundary homological vector fields. So you should quantize this function to some operator. And if you do things in the correct way, the state associated to the bulk is annihilated by the operator associated to the boundary. So this tells you in which sense this theory is defined. So essentially the idea is that the physical vector space associated to the boundary should be the cohomology with respect to this operator, and well, and the state associated to the bulk is really an element of cohomology. Things that turns out to be more interesting if you take into account the fact that critical points are often not isolated. So this then situation becomes a bit more interesting. You not only have a vector space associated to the boundary, but you also have some other space that parameterizes critical points. And then if you do things correctly, it turns out that the state associated to the bulk satisfies this more complicated equation. This is operator associated to the boundary, and this is so-called BV Laplacian that is associated to the BV structure. Okay, in the infinite dimensional case, it has to be carefully defined, but this is the general equation you expect. And this equation also behaves well under gluing. Now the point was, okay, are there examples where this can be achieved? Well, there is one example already published by Pavel Nyov and Anton Alexeyev. This is one-dimensional topological theory, some sense it's some version of one-dimensional Chern-Simons theory, where you can do everything also non-perturbatively. You can really do canonical quantization, and you get this equation. And then there are several more non-published examples we already have. For example, for topological field theory, where you can really make sense of this integral, and you can really find out this psi satisfying this equation. And actually, just to show you that things are not so terrible, essentially, the way you have to compute the psi is just by using the usual Feynman graph you might be used to if you think in terms of Chern-Simons theory, Poisson-Simon model. But now the only thing, in addition, that you have a boundary and you have some arbitrary number of points you can put on the boundary. This is essentially the only thing you have to compute. And maybe now the idea is that what is somehow the categorical version of this BV theory, quantized BV theory on boundary. So the idea is that now to a d-1 manifold sigma, you should associate a complex, now not just a vector space, but a complex. And to a D manifold, you should associate a state in this complex annihilated by the boundary operator, plus functorial property. So again, should be a functor from some coordinating category to this category of complexes. And the idea, okay, why should this be interesting? So the idea is that, okay, you want to compute some field theory on a manifold with boundary, or actually on a manifold without boundary. And the idea is like to do whatever you usually do in topology. You just cut down your complicated manifold into little pieces and try to make local computation, and then glue things together. So one partial result, we start having, for example, is how to do Chern-Simons theory, perturbative Chern-Simons theory in this setting, and it seems to work. I mean, well, we already done the exercise for BF theory. It works, but okay, that's not very interesting. But it seems to work also for Chern-Simons theory. So eventually, it tells you that, for example, it's enough to compute Chern-Simons theory on a solid torus in the perturbative setting, and out of it, you should be able to compute the invariance for every free manifold, or at least for rational homology spheres. Just out to now just finding integrals on the configuration space of points on a two torus. Okay. So
questions or comments? So there's a coffee, I guess, outside. Thank you, speaker again.